second. Okay. Can you hear? Sorry, can you see my screen?
Yeah, thank you.
Okay. Okay. Um, so I'm starting with some general information about microcontroller units here. Most microcontrollers have serial interfaces to communicate with supporting devices. I will give some examples at the end of the presentation. In larger systems, the microcontroller units might be slave devices, subordinate devices to PCs, to embedded Linux systems. In those cases, they use serial interfaces to transfer data, transfer information to the um, higher level systems, to PCs and Linux devices. I wanted to point out the characteristics of most of normally used serial interfaces and focus on the differences, advantages, and disadvantages. Um, with also the focus on the practical implementation, including for projects. I will be mentioning logic families. I will be mentioning specific chips, specific integrated circuits that use these serial interfaces. I wanted to start with just some general information about data and how serial interfaces came to be. Data in microcontrollers is processed in parallel format in data words of different width. The microcontrollers are pretty much defining themselves by the amount of bits that they can process in parallel. The problem now is how to transfer, how to get this data out of the microcontroller, how to do something with this data. And as long as the data is in parallel format, it requires a separate connection per bit. That means the packages for the integrated circuits are being larger. The wider the data width becomes that is being processed inside those microcontrollers. It affects the size of connectors and it affects the size of cabling. There are some issues, for example, about the complexity of systems that happens when the packages, integrated circuit packages, become bigger. Traditionally, integrated circuit packages have the pins on the outside of the package. For systems that have 64-bit or 32-bit buses, parallel buses, more and more of those integrated circuits are switching to a different type of package, which has the connections under the chip. Those are called ball grid arrays, BGA packages. One issue with these BGA packages is that they're difficult to solder and desolder, and they're also difficult to test. Usually, one requires several layers of circuit board layers to distribute the pins to the rest of the circuit board. So usually, once you get to a size, once one gets to a size where a BGA package is required, at minimum a 6-layer board is necessary. And yeah, that makes debugging the board, that makes testing the board more and more difficult, and the project more complex. It takes a longer time to develop. So that's what I meant with affects the size of integrated circuit packages. Connectors and cabling, there is an issue there where the cabling increases the cost of the cables, of course, because copper is becoming more and more expensive. So if you have 8 wires or 16 wires or 32-bit wires, it makes a cable more expensive. And depending on the application, that makes it not cost competitive anymore. The same with connectors. The more pins connectors have, the more expensive they become. And it also has an effect on reliability. The more pins a connector has, the more the chance is given that one of those connections will malfunction. Parallel interfaces are often implemented between components on the same circuit board when highest transfer speeds are required. Data bus under tightly controlled conditions. This is typically on a circuit board, data buses, address buses to memory that has to be accessed in a very fast way. We all know on PCs, DDR, for example, DDR memory, different types of DDR memory. And when I'm saying under tightly controlled conditions, oh, sorry. Yeah. Under tightly controlled conditions, that of course means the length, because the transfer speeds are so high that the length of the traces on the circuit board has to be equal, because it has to be guaranteed that on every pin, on the signals on every bus line have to arrive at the targeted device, have to arrive at the same time. And the speeds that we're talking about are picoseconds. So basically at those speeds, like even picoseconds count. So sometimes when someone looks, if you were to look at a circuit board for PCs, for example, you will notice that some of the traces will make weird or strange, unnecessary curves, turns. This is done for guaranteeing that all lines, that all signals arrive at exactly the same time. Parallel interfaces to off-board devices used to be common in microcomputers, Centronics, ATS, SCSI, but have been mostly replaced by serial interfaces. People who have been building PCs for the last 20 years probably are aware of the old style ATA interface that used a 40-pin ribbon cable. Similar with the old style SCSI interface, also pronounced SCSI interface. Those were even wider. Those had 50-pin cables. And with increasing speeds, these cables, those interfaces, have just become not cost effective, not cost competitive anymore. In this slide, I want to point out two statements that I'm making here. Serial interfaces are slower than parallel interfaces. That is kind of that is a logical conclusion. Parallel data must be serialized for transfer. Instead of transferring one data word in a single step, it must be transferred in 8, 6, or 32 steps, depending on the width of the parallel data that we're trying to transfer. So for up to about the year 2000, 2010s, it was just, oh, sorry, accidental mouse clicks. It was common that we were trying to make the interfaces more parallel, increasing the bit width, putting more wires into the parallel interface, until at some point in time, it was not cost effective anymore. We were hitting limits in technology. And that's when the second statement came in. Serial interfaces are faster than parallel interfaces. At some point in time, the data rates became, the possible data rates became so high that having cabling capable of sustaining these data rates in parallel connections was just not practical anymore. It is sometimes done for offboard communication, but those cables are not in the range of dollars. They're in the range of hundreds of dollars. Just because it is so difficult to manufacture a cable with the amount of precision that it can transfer parallel data for more than a few meters at the speeds that we're talking about, which is gigabits. Theta 2, for example, is 6 gigabits per second. Ethernet, we're talking about, you have not just gigabit Ethernet, we have 10 gigabit Ethernet that is still running over cabling, over Cat5 or Cat6 cabling. And I've put an image here into the presentation just to demonstrate this. That's an eye diagram. The eye diagram is a tool for identifying the quality of a differential twisted pair connection on a single twisted pair of wire. We're going to talk about differential connections later. What I'm trying to point out here is just even for a single serial data connection, at the speeds that we're talking about, it is difficult to get a good connection. Trying to do this for 8 cables in parallel, or even more, 16 or 32 cables in parallel, is just not practical. It's not cost effective. So because of the high data rates that are possible nowadays with the semiconductors that we are using, parallel cables or parallel connections have become obsolete. Good question. Any questions about what I'm saying here? No questions. Okay. Okay. So that is the reason for why serial interfaces are a thing, why we're implementing serial interfaces. And I want to start with how this is being done. How is the data coming from a parallel connection to a serial interface? Usually for the microcontroller circuitry that we're talking about, this is done using shift registers. I have in the image, I have a 4-bit shift register. In this case, it's a serial data in, parallel data out shift register. Shift registers are constructed from flip-flops. In this case, these are D flip-flops. I want to, just a second. I want to point out for people who want to build a shift register from flip-flops for hobby purposes, for example, or for demonstration purposes. The logic family or the logic devices that could be used for this are the 74HC74 and the 74HC175. Those are some of the logic chips that have shift registers that have flip-flops, D flip-flops, that can be used for this purpose. Of course, there are also logic chips that have complete shift registers built in. We're going to talk about those later at the end of the presentation. In general, when I'm mentioning logic chips from logic families, I generally talk about the HC family, even though there are many, many more. Simply because it is currently the most easily purchasable, the most easily accessible logic family. There are specialty applications for the HCT family. There are applications for the LVC and LVT family. But if I just want to point out logic chips that can be used in projects, I generally use the HC family. Okay, so shift registers. Serial data is sent and received as a stream of bits. It can be 0 or 1. Can be these two levels can be represented by different types of signals, voltage levels, electrical currents, frequencies, for example, that I hadn't mentioned before. It used to be in the age of teletypes, the 20 milliamp current loop used to be very common. Nowadays, generally, we use 5 volts and 3.3 volts for signaling in microcontroller circuitry. Of course, for microprocessors, the voltage levels generally tend to be going lower. Simply because the lower the voltage, the less waste power dissipation we're getting in full high-speed microprocessors. In microcontrollers, generally we try staying at around, at the moment it is about 3.3 volt voltage levels, which is the supply voltage for most modern microcontrollers. The receiver of this bit stream does not know when a data bit is valid for sampling. For this reason, there must be a mechanism to synchronize the bit stream to the receiver shift register hardware. And that you can see that in the image that I'm showing. There's a clock signal. This is the first time where a clock signal shows up. Basically, a clock edge is telling the register to take over, to accept the value that is on the serial data input. In this case, for the flip-flops, that's the D input. I'm continuing with this topic. Serial interface, which provides a separate signal line for bit synchronization, is called a synchronous serial interface. There are a little bit more complicated explanations, but for the interfaces for the microcontrollers that this presentation is about, basically that is the definition. We're calling it a synchronous serial interface if there's a separate line for bit synchronization. So basically, in the synchronous serial interfaces or synchronous serial buses, a separate line is telling the receiving device, is telling the receiving client when a bit is valid. It is supposed to be shifted into the receiving shift register. That is a big difference between the synchronous and later the asynchronous interface. In the image here, you can see the clock and the data signal. In this case, a rising clock signal is indicating when the data is valid. It doesn't have to be a rising clock signal. This is just an example in the image. It could also be a falling clock signal. The separate signal line is called the serial clock line. The serial clock indicates when a bit on the serial data line is valid for sampling, usually by a signal level transition. That is the edge, in this case, the signal edge from the rising edge from low to high. The big advantage of the synchronous serial interface is that the speed is not really important. The receiving device will accept a bit when it sees the rising or falling edge of the clock signal. That's it. It doesn't care how much time has passed in between. So it is possible that the clock can vary, can even stop for a short period of time. For example, when the serial interface is implemented by hand, not through a actual device or peripheral device in the microcontroller. We're going to talk about that as well, what that means to bit bang a serial interface. That's the colloquial term for this, doing this. And if the serial data communication is interrupted for a short period because something with higher priority is happening, it does not matter to the receiving device. So even in the middle of a data word, it is possible for an interruption to happen. And the receiving device will just patiently wait for the next rising edge to take over, to accept the next bit. I'm mentioning, this is a little bit of a sidetrack here. I'm mentioning the Manchester code, a self-clocked synchronous interface over a single wire is possible. Manchester code. It is often being used as an example for as a classic example for a self-clocked signal. It is more interesting here for a different reason. The Manchester code is an encoding scheme that makes it possible to transfer large amounts of data that has the same polarity. For example, you're trying to transfer 10,000 ones. And the receiver needs to be isolated. What the Manchester code does is it will completely turn this DC signal, a signal that is effectively a DC signal, it will turn it into an AC signal. which makes it easy to electrically isolate by using a transformer. That's just a little bit of history. The Manchester code was initially used in very early versions of Ethernet. I'm mentioning this name Manchester code without explaining exactly what it does. It's easy to look up. There is lots of information on Wikipedia if someone is interested. Okay, now that I've explained the basics of the synchronous communication, which essentially I want to point out the synchronous communication means there's a separate line for the clock signal, a separate line that tells the receiver when a data bit is valid. So now we're getting to the asynchronous communication. The asynchronous communication does not have a separate clock line. But the receiver still needs to know when a bit is valid. So that is called an asynchronous serial interface. The classic version of use of an asynchronous serial interface is operated by a UART device. UART literally stands for Universal Asynchronous Receiver Transmitter, which also is part of a later slide. The UART device implements a start-stop asynchronous interface defined by an added start bit and stop bit for synchronization of a data frame. The data frame is usually a byte. Most people probably have heard of a UART. They've heard of serial interfaces that are asynchronous. The start and stop bits have opposite signal level. This is important. If you look to the image to the right, to the upper right, it's explained there. The start bit is 0. The stop bit is 1. The effect that this has is there is a forced signal edge. Every time when a new byte starts, there is a guaranteed forced signal edge, a negative falling signal edge, between the stop bit from the previous byte and the start bit of the next byte or data frame. The receiver will expect this falling edge to start its own clock generator. Its own clock generator is also called a baud rate generator. It will start sampling the first bit after 1.5 clocks, bit cycles, bit speeds bit times have passed. And from then on, it will start sampling the data line every bit time. That is demonstrated in the image in the upper right-hand corner. On the bottom, where it says serial receive. The addition of start and stop bits reduces efficiency. 10 bits must be sent for every byte. So that is a drawback. The advantage of the asynchronous communication is it does not require a clock line. It can be transferred basically just on a single wire on a single data channel without the need for an additional clock channel. The disadvantage is in this case that there's an overhead. The overhead is 2 extra bits. The transmitter and receiver must use the same fixed bit rate with at least 2% accuracy. There is a lot in this sentence, and I will have to point a number of things out here. So the first question that I would expect if this was an actual in-class lecture, the first question that I would expect, why 2%? 2%, it is more or less like a rule of thumb, but it's 2% because we're transferring 10 bits. We're trying to sample in the middle of each bit. So the sample point is not allowed to shift more than half a bit time. So if we're 10 bits, and it can't be more than half a bit time, so we have 20 half bit times. 1 divided by 20 is 0.05, so that's 5%. So now we have a transmitter and receiver, both can be off in the opposite direction. So they have to be accurate to 2.5%. So now we are taking 0.5% off as margin, and that's how I'm getting to the 2%. That is generally the rule of thumb. That's where the 2% number comes from. The next item is must use the same fixed bit rate. What is the fixed bit rate? There's a lot of history in this. The asynchronous communication was the first implementation of long-distance communication systems. This was done in the 1950s. The standards for this were done in the 1950s, 1960s, when computer systems were trying to communicate over telephone lines. Telephone line communication was done through modems, modulator, demodulator units. And the European standard V21 and the Bell 103 standard started out with a speed of 300 bits per second, or baud in this case, 300 bits per second duplex in both directions in one telephone channel. And as it happened, all the commonly used serial interface speeds are divisible by 300. So common speeds of this fixed bit rate are, for example, 9600 bits per second, 19,200 bits per second. It usually doubles, 38,400 bits per second. Anybody who has used a terminal program or anybody who has used USB to serial converter in a hobby project has probably seen these numbers. And on the lower end, so it started with 300 bits per second. The next common one was 1200 bits per second, 2400 bits per second. That's where it all came from. There's a little bit of history in there. But the typical bit rates for asynchronous communication are somewhat fixed. It is possible to use different bit rates, but it is unusual. For example, on a microcontroller, if a microcontroller is trying to talk to a PC and is trying to transmit data, a very often used transfer speed is 115,200 bits per second. It sounds strange, but it is divisible by 300. And it just developed over time that these speeds are the standard speeds. The next consequence of this is that the entire system sometimes, especially in older microcontrollers, is driven by this need for the fixed bit rate and by the accuracy, by the 2% accuracy, meaning that you will find when you're looking into crystals, circuit board crystal oscillators, that you will find sometimes very strange crystal frequencies. For example, 1.8432 megahertz or 3.6864 megahertz. Those strange frequencies happen to be divisible in a way that they can be used for generating these typical serial asynchronous bit rates. If people have worked with older microcontrollers, for example, the 8051 series, which I believe is still fairly popular in Europe and also in similar in Eastern European countries, sometimes you will see a strange crystal frequency 11.0592 megahertz. Same reason, except in this case, a divider by 12 is involved because the 8051 has a 12 division machine cycle clock. So when you see those strange crystal frequencies, usually the reason is because the system is trying to get an exact specific bit rate for asynchronous communication right. Another issue here is that in order to get this accuracy, the 2% accuracy properly done, it is often required to implement a crystal oscillator in the system, in the microcontroller system. Most modern microcontrollers have fairly accurate RC oscillators on chip. And my recommendation would be, if you're starting to design a system with that needs to connect over UART, RS-45, RS-232 interfaces, and you are trying to use the internal RC oscillator, then read very, very accurately in the data sheet how accurate this RC oscillator actually is at the temperature extremes, at -40 degrees, at +85 degrees. Sometimes an RC oscillator that is advertised as 1% accuracy is not actually 1% accurate. It is sometimes, if you or if one looks at the temperature extremes, it might just be 3% accurate. So it cannot be used for asynchronous communication. And in that case, a crystal oscillator is required again. Generally, if you are wanting reliable communication for to PCs or on buses like Modbus, RS-45, I would always recommend implementing a crystal oscillator on the microcontroller, even if the cost is increased. Sorry, there was a little bit of a lengthy discussion or a lengthy text for just one sentence here. Okay. Next item, the bit stream of zeros and ones is represented by different electrical signals for each bit state. We had mentioned that before. Usually, it is a voltage. So usually we're saying 0 volt is 0, 5 volt is 1. And in more modern microcontrollers, it is 3.3 volts. In microprocessors, it can be 1.8 volts. It can be lower than that. Serial data signals that are signal lines that are referenced to system ground are called single-ended. This is the natural state of a serial bus, serial interface. Usually you have a microcontroller on a circuit board, and everything on that circuit board is referenced to system ground. If the term system ground sounds somewhat nebulous, somewhat obfuscated to you, just imagine if you're powering your circuit board, your microcontroller, from a battery. Generally, system ground is simply the negative terminal of the battery. And everything is referenced to that negative terminal of the battery. Most signals on the circuit board, most signals that are interfacing to the microcontroller are single-ended. Serial data signals that are the result of a voltage subtraction between two signal lines are called differential signals. There's a reason, and actually I'm reading the next item here. Differential signaling offers improved noise immunity over single-ended signaling, but requires additional hardware. Single-ended is used for short distances. Short distances, of course, means usually on a circuit board, for example. And most importantly, on a circuit board that you're designing, if you're becoming engineers, if you're designing the circuit boards, or if you can talk to the designers of the circuit boards, then the noise environment is under control of the designer. For any kind of serial interface, serial bus that leaves the circuit board, goes to a cable, for example, to a different device, to a PC, it goes to a different room. At that moment, the noise environment is not under control of the system designer anymore. Sure, it can be specified that the cable has to be shielded, but you don't know what the user, one doesn't know what the user is doing with the connection. So that is kind of the difference between on circuit board and off-circuit board systems. And what is happening here is that the differential signal is subtracting. It needs a wire pair, so it needs one extra wire over a single-ended connection. But what happens is that any kind of noise that is impacting the connection is showing up on both of these wires in the same polarity. The differential driver is subtracting the signals. And the big benefit is that noise signals or ESD, anything that happens to the data signal that would destroy a single-ended signal is simply subtracted. It is eliminated in the differential driver. So that is the reason why pretty much every modern serial bus, every modern high-speed and off-board serial bus is using differential signaling. USB is using differential signaling, RS-45 is using differential signaling, Ethernet is using differential signaling. Pretty much everything is that every serial interface that goes off-board uses differential signals because of this vastly increased noise immunity. Even if the cost is an additional wire. So in differential signals, we're talking about wire pairs. And in the image to the right, the middle image, or the lower image to the right, you can see that these wire pairs are usually twisted. Also to reduce noise, to make sure that this feature that the noise signal that appears impacts both wires in the same way, so that it can be subtracted out in the differential driver or receiver in this case. So yeah, that is the differential data transmission. Single-ended data transmission. So I mentioned that on the circuit boards, the natural state on a circuit board is single-ended. So buses that are intended to operate on a circuit board close to the microcontroller generally are single-ended. And these single-ended drivers can use push-pull circuits or open drain circuits. There are advantages and disadvantages. I don't want to be like too nebulous here. When I'm saying serial interfaces, serial buses that are operating close to the microcontroller, in effect, for this presentation, what I mean primarily is SPI interface and the I2C interface. You've probably heard of those before. So these two interfaces generally use two different driver schemes. The SPI interface uses push-pull outputs. The I2C interface uses open drain outputs. Both have advantages and disadvantages. The push-pull outputs that you can see in the image in the upper right corner actively drive both 0 and 1 states to the desired voltage level. So this creates two dominant bit states on the bus. So both levels, the high level and the low level, is driven by an output. This is good if you're trying to transmit signals fast. This is bad if you're intending to use this as a bidirectional bus line, because then there's a risk that due to coding error, other error conditions, the two outputs can drive against each other, if one output is trying to drive a signal high and another output that is connected to the bus is trying to drive the same signal low, then you're getting a large error current. A large in this case would be 40, 50 milliamps, which is large in terms of microcontroller circuitry. So you have the advantage of the higher speeds and the disadvantage in bidirectional buses of possible high currents in under error conditions. The other option is the open drain output. And that means one signal is driven and the other signal is pulled, usually by pull-up resistors. It could be pull-up resistors or pull-down resistors, but it is not actively driven by MOSFETs or transistors. This creates a dominant and a recessive bit state. And both methods, and we're going to see that when we're talking about SPI and I2C, results in different bus control options, power consumption, and data rates. Generally, because the open drain output, so the open drain output is more suitable for many devices on the bus, on a single-ended bus. But the speed is generally limited and depends on the size of the pull-up resistors. If the pull-up resistors are low value, then the speed can be fast, but at the same time, the power consumption increases. Okay, I'm going to the next slide. Serial bus basics. A serial interface can create a serial bus to many bus nodes or to a point-to-point connection or a point-to-point connection to one device. Serial bus must provide a method to address bus nodes or identify message types. Usually we think of a serial bus as something that where every bus node can be addressed. It's kind of normal to think of that a device that is on the bus can be directly talked to. That is not always the case. It is the case for example, for the I2C bus, but the CAN bus, for example, only knows message types, message IDs. Because there were two different philosophies behind this. The CAN bus was originally designed, and we're going to talk about that later. The CAN bus was originally designed in an automotive environment as a broadcast bus. And every device sitting on the bus was supposed to listen in and listen to specific messages and then filter out what kind of message was important to it. Addressing specific bus nodes was not important. Later, it turned out that yes, it actually is important. And so especially for the CAN bus, there's a number of added-on protocols that have been put on top of the base CAN bus message framing that allow for addressing specific nodes, just as a little bit of background information. A serial bus can operate in master client, multi-master, or multi-drop mode. I think that is relatively clear. Master client means there is one bus master, generally a microcontroller. But if our microcontroller, basically that we're designing for, if our microcontroller is reporting to a device that is higher up, to a PC, to a embedded Linux system, for example, our microcontroller system might be the client. But for systems like the SPI bus, the I2C bus, generally the microcontroller is the master. So the microcontroller is the master. A number of peripheral devices are the clients. Could be just one device, it can be several. But the master device is asking for information or issuing commands to the client device and getting responses back. A serial bus can be multi-master. That means that there are several devices on the bus that can just randomly start transmitting. The problem with this is that in this case, there must be a method to figure out so that the different masters can negotiate and can find out if there's a bus collision happening. If two masters are trying to transmit at exactly the same time, they need to find out that this has happened, and they need to find out who gets priority. The CAN bus, for example, is by design a multi-master bus. And we can talk about how that is being done at a later slide when we're getting to the CAN bus. Multi-drop basically just means that it is purely a broadcast bus. There is one master in the system that is sending signals, and there are receivers in the system that just receive data, more than one receiver that just receive data but never respond. This is why, for example, the RS-232 bus can be called a bus because multi-drop is possible, but really it is not a bus. It is just a point-to-point connection. We will be getting to the RS-232 later. The data lines used by the serial interface can be unidirectional or bidirectional. Bidirectional data lines, just a second. Okay, I had a cat here showing up. Bidirectional data lines may need precise bus turnaround timing. This is the issue. We talked in a previous slide about two dominant states. This is possible on single-ended interfaces, but also on in differential drivers, that both states, 0 and 1, can be dominant. And the problem with this is that if the system is bidirectional, it's also sometimes called half duplex. If it is bidirectional, then the master is issuing a command, and then it is occupying the bus while it's doing it, actively driving the bus in both directions. It is issuing a command to a slave or a request to a slave, and the master must relinquish the bus, must turn off its driver before the slave starts transmitting. If that does not happen, then you can have a situation again where two drivers work against each other, which creates a relatively large current, 50 milliamps, 100 milliamps. Generally, the driver chips are designed to sustain this. They don't break. Especially CAN drivers, RS-45 drivers are very robust. They don't break, but it is an error condition, and it increases the power consumption. And most importantly, because this can happen in buses that are bidirectional and have two dominant states, the power supply for the microcontroller, for the drivers, must take it into account, which usually means using a switching power supply, which might increase the cost of the device. Yeah. Serial bus electrical considerations. I wanted to quickly talk about that a little bit. The phrase on-circuit board is used to indicate that the electrostatic discharge, electrical noise, and transmission line environment are under control of the developer. So the buses that I had mentioned before, SPI bus, I2C bus, the synchronous buses that are really meant for onboard design, short distance communication to a microcontroller. The environment, they don't have, these buses do not have error corrections. They don't have any error detection mechanisms, simply because they expect that they will be deployed in a situation on circuit boards where the developer is in charge of making sure that no noise, no electrostatic damage or problems can occur. And if that is not practical enough, for example, making sure that no electrostatic damage occurs might be as simple as the designer saying that the circuit board needs to have an enclosure. It needs to have a case so that no user can actually touch the circuit board. That might be enough. The electrical noise environment might be enough. It might be enough that there's a good ground plane, that one of the layers on the circuit board are a decent ground plane. It can be complicated, but sometimes it can just be very simple. the transmission line environment. Transmission line is something that is a more complicated topic. When I'm saying a transmission line, that is, I don't mean a power transmission line. I don't mean something like the kind of transmission lines that you see on on pylons that are out on the field. What I mean is a transmission line is generally a connection that carries a digital signal or some kind of high frequency signal that is high frequency enough that a certain transmission line effects have to be taken into consideration. I have an example in a picture in the upper right corner. When I'm talking about a piece of wire or even a trace on a circuit board, it is not just a trace on a circuit board. It is not just an ideal connection. Even a trace on a circuit board, it has a capacitance. It has a capacitance to ground. It might have a capacitance to other traces that are close by. It has an inductance. It has a resistance, an isolation resistance. It has a resistance, of course, by itself, like an ohm, a resistance that dissipates power. And usually at low frequencies, you don't really have to worry about transmission line effects. But if you're using higher frequencies, and high data rates usually result in high frequency signals, in possible high frequency signals, you have to start transmission line effects into account. My rule of thumb is if the wavelength of the AC signal approaches a hundredth of the trace, roughly a hundredth of the trace length of the signal of the trace length on the circuit board of the signal that you're trying to transfer, you have to think about transmission line effects. What does it mean? So, for example, you are trying to use a 10 megahertz. You have a 10 megahertz signal. You're using an SPI interface at 10 megahertz. At 10 megahertz, you have a wavelength of 30 meters. A hundredth of that is 30 centimeters. So if your trace length on the circuit board approaches 30 centimeters, start thinking about transmission line effects. The effects are usually is a routing of the trace, the ground plane under the trace, the closeness to other wires. It's just a rule of the thumb. And if you're not specific into circuit board design, this might not, what I'm saying might not mean much to you. But you are trying to get, if you are trying to get into circuit board design, we can possibly talk about designing circuit boards for high frequency communication lines in more detail in possibly another lecture, or you can send me an email, for example. Okay, next item. Circuit board system ground is different from chassis ground and earth ground, and there can be large voltage differences between them. Ground loops can be a problem. Therefore, galvanic isolation is often needed for long-distance serial bus implementations. System ground is generally the ground that you have on your circuit board. I was simplifying it by saying it is basically a ground plane that is connected to the negative terminal of a battery. So often, of course, microcontroller systems are not powered by batteries. But the system ground can be different. The definition is different from chassis ground. The voltage level can be the same as chassis ground. You can, if you wanted to, you can connect earth ground directly to your system ground. It's not often being done, but you could do that. But there's also a possibility that there are large voltage differences, especially if you're connecting a serial bus to a different device that is a long distance away. You never know how an electrician has wired up a house. Sometimes they make mistakes, and there's, for example, between outlets, even in the same house or in the same building, there are outlets where the neutral and the earth ground are connected in the wrong way, and people don't notice it because nobody ever uses devices that are connected between buildings or between rooms in the same building. However, if you're connecting earth ground, for example, between on a signal cable to the shield, for example, the shield of a signal cable, and route that to a different room in the same building, and that room has a different potential, voltage potential on that earth ground, you might get fairly large voltage differences between the different earth grounds. If it is hooked up in the wrong way by the electrician, there is the possibility that you have the entire AC voltage as voltage difference. So the mains AC voltage, in your case, it would be 220 volts or 230 volts. There could be a potential difference of 230 volts. In order to avoid that, you need isolation. Generally, buses that might be connected to different earth grounds on both ends of the connection are isolated. They're being isolated. Ethernet, for example, right from the start, was designed as an isolated communication bus. That's why I have the picture on the right there, which is actually an Ethernet connection. It shows an isolation transformer. At the time when Ethernet was when Ethernet was developed, the easiest method to isolate two ends of a connection was through transformers. In our situation, for microcontroller circuits, we most likely would be using optocouplers for isolation. But I just wanted to point out that isolation can be done with transformers. Isolation can be done with optocouplers. It is an important item. Ground loops is a different type of problem. If you have a ground connection on a long wire, or if you're routing your ground line on several different connections, for example, you have two cables, and you're routing the cables with a certain amount of distance between each other. And you're connecting the ground, the shield ground, for example, on one end of the connection, you're connecting the shield ground on the other end of the connection. You're creating a loop. What happens is that in the distance in the area between those two cables, magnetic fields will occur. It could be magnetic fields from motors, from lighting, all kinds of different magnetic fields are pretty much everywhere where there's electricity. These magnetic fields will induce a current into this loop. So now you have a current circulating between the grounds. And what that does is it creates a voltage drop. Because the cables, or even the shield cables, they're not ideal. They have an ohmic resistance, even if it's just a few ohms. So suddenly you're creating a voltage drop, and that voltage drop can affect your signal. Like, that's the danger with ground loops. People who work with audio equipment probably have heard ground loops happening. In audio equipment, for example, if you have a microphone amplifier or a big speaker setup, it usually appears as a hum, as a 50 hertz hum in the recording or on the speakers. Anybody who has worked like with long distance audio cables probably has heard that before. That is, and this is in audio systems, but it also affects digital systems. So galvanic isolation is a thing, and that is more or less easy to do in different types of buses. Okay, next slide. Oh, that was one too much. So I'm just, this is kind of like the introduction into the differences of serial buses. I just want to summarize again. So a serial interface can be intended for short distance on-circuit board or off-circuit board operation. Off-circuit board operation usually uses differential drivers because of its increased noise immunity. On-circuit board usually uses single-ended buses. A serial interface can be a synchronous interface or an asynchronous interface. Again, synchronous interface generally means, like for the serial buses that we're talking about, a synchronous interface is one that provides a separate line for the bit synchronizing clock. If there's a separate clock line, it is generally a synchronous interface. It can use single-ended or differential signaling. Its bit states can be dominant or recessive, and both types have advantages and disadvantages. Its data lines can be bidirectional or unidirectional. Again, a quick comment to bidirectional. In a asynchronous interface environment, generally we call this half duplex. If the interface is bidirectional, it can also be called half duplex. The serial interface can create a master client or a multi-master bus or a point-to-point connection. It can be easy or difficult to electrically isolate. So these are items that I just wanted to point out that create different characteristics of the different serial buses that we're talking about. If you're ever wondering, why are there so many different types of serial buses? Each type of serial bus has specific advantages and disadvantages in specific situations. Okay, now I am focusing on the serial buses in microcontrollers. I have an image to the right here. This is actually taken from the microcontroller that is sitting in one of the more popular, smaller microcontroller boards. It's an Arduino board. Hobbyists probably have heard of the Arduino boards. It's an 8-bit, it's kind of an obsolescent 8-bit CPU. But I picked this image because in the lower half or lower third of this image, you can see the USART, the SPI, and the TWI. So the USART is, there's an S included, but it's a UART, it's an asynchronous, the universal asynchronous receiver transmitter. There is the SPI interface, serial peripheral interface. And in this case, the I2C interface is called a TWI, which is another name for it, the two-wire interface. The UART is generally being used for off-board communication, and RS-232, RS-45, J1708 standards are using the UART peripheral. The SPI bus or interface is a synchronous interface. Usually it's called 4-wire or 3-wire bus. 4-wire, well, we're talking about the SPI. We're going to talk about it. The I2C inter-integrated circuit, in this case, it's also called the 2-wire interface, is a synchronous serial interface with a bidirectional data line. Only requires 2 lines, often called a 2-wire bus. There's a similar bus that is called SM bus, which is generally what you can find in PCs. It's like a minor control bus that is in PCs. It is not quite identical to I squared C, to I2C, but it is similar enough that most devices will work on a PC will work with an SM bus driver if you hook it up to an I squared C device. This also affects, for example, embedded Linux. I'm talking about a PC, but it also affects embedded Linux devices. If an embedded Linux device has an SM bus driver, that usually means you can connect I squared C devices to it as well. There are three other types of serial interface that are implemented in mid to high-end microcontrollers. CAN. We're going to talk about CAN. CAN is fairly popular. It comes from the automotive world. There is a J1939 standard. There is for both the NMEA 2000 standard, RVC standard, are based on the CAN interface. There are other protocols. There's a CAN open protocol that is basically put on top of the original CAN engine or the CAN interface inside a microcontroller. There's a USB bus and Ethernet, which we're not going to talk about in this presentation. USB, we're using it every day, but in many embedded systems, it is actually not a very useful bus. It is primarily useful for connectivity to larger PCs and connectivity to higher end devices. The problem with the USB bus is that it's very PC centric. The setup is very PC centric, but most importantly, the distance. USB has a fairly limited cable length, a maximum cable length. There are USB repeaters, but interfaces like, for example, CAN, like RS-45 or Ethernet, can go 100 meters or longer. And those are cable lengths that USB typically cannot do. Of course, if you need a connection to a PC for loading data, loading configuration data, retrieving log data, then of course a USB bus on a microcontroller is immensely useful. This presentation will explain the difference in use cases of UART, SPI, squared C, and CAN. And again, in this case, not USB, not Ethernet. We can talk about that later in a different presentation if there was interest. I'm starting with the UART device. The term UART refers to a peripheral device. It is not the name of a serial bus. It is basically a peripheral device inside a microcontroller. For the early microcontrollers, it can also be a separate device that is sitting outside the microcontroller. Early and smaller microcontrollers do not have a UART device, like 8-pin, really, really tiny microcontrollers do not have a UART, but most do. It is a very basic, fundamental serial interface for most types of off-board communication. And so any microcontroller with more than 20 pins at a price with more than 50 cents or $1 will have a UART peripheral inside. A UART can be used to implement I should have said here asynchronous serial buses. RS-232, Modbus over RS-45. There's a number of industrial buses. Modbus is one of them. There's Profibus. There's a number of other industrial buses that are using RS-45 and implemented by a UART. A UART is the device that is just essentially organizing the shifting of the parallel data into a serial data in an asynchronous way. Buses like Modbus do more in software. So the features of bus turnaround, of error correction in Modbus implementations is done in software. So there is a significant amount of software effort required besides just loading up a UART with data. Historically, UARTs were used for long-distance communication using modems, demodulators. I talked earlier about modem standards when I started about asynchronous communication. It was basically one of the first types of serial communication. Many UART implementations still have modem shaking signals. In the image to the right here, on the lower right, I have, for example, device A, device B. There's a CTS, RTS signal, CTS clear to send, RTS ready to send. Those are outputs and inputs. There's a number of other control signals for a UART connection that only make sense in the context of modems. And you have possibly seen them before because they're still being broken out. They're still being used on USB to serial converters. And they're labeled, for example, DCD, DTR, and even just from the names, DCD, data carrier detect, the word carrier means this is the dial tone essentially in a telephone line when a modem is trying to connect. DTR, data terminal ready, for example. Those come from a time period when the modems were connecting not just personal computers or home computers, they were connecting data terminals. And so there's a lot of legacy naming in these names. And really the important lines are TX and RX, transmit and receive. Those are the usually accepted abbreviations for the transmit and receive lines. Sometimes you use hardware handshaking, which is the clear to send and ready to send signals. Most of the other signals, ring indicator, for example, if you've seen RI on one of the USB to serial converter devices, if you've seen RI, that stands for ring indicator, for when the telephone is ringing. These are all obsolete signals. They're not being used anymore. You can use it sometimes as general purpose GPIO lines from a PC if you really dig deep into it, if you're really trying to find out what to do with these signals. Basic error detection can be activated, and by that I mean there is a parity bit. Usually a UART will allow for using the 8th bit as a parity bit, which is essentially an addition of the 7 preceding bits. This is not often being done. Usually you do not use, or in most implementations, an error correction on the data frame level is not being done in UART implementations. What is being done is data is being packeted up, is being put into packets, and then our cyclic redundancy check, a CRC, this is called a CRC, is being run over each packet as a means of error detection. There are protocols, for example, NMEA 0183, which is the protocol that GPS modules are using. If you go to AliExpress, if you go to other stores and you buy a GPS module, you know GPS, Global Positioning System, there are relatively cheap modules on the market that you can directly connect to a UART. And these modules use the NMEA 0183 format. This format has a checksum. That is another method of error correction, but it's a very primitive method of error correction because a checksum will just add up all the characters of one line and basically sum it up and turn it into a byte. And it will only, it usually detects single bit errors. A CRC, a cyclic redundancy check, is a little bit more complicated, but it can detect a whole different range of errors. It can detect many different types of bit errors. So generally, implementations like Modbus use a CRC for error checking. And if you're interested in CRC and interested in using a CRC for securing your data communication, there's lots of implementations, and I could also provide some sample code. Your professors probably will talk about it at some point. So basic error detection is there, but it's not really being used. The naming designation of transmit and receive lines is a frequent source of errors. The original naming was intended for data terminals and data communication equipment. The reason why it is a frequent source of errors is because it is not always clear which one is an output and which one is an input. For example, if a device is labeled as data communication equipment, so in the early days, this was a modem. If a device is labeled as that, then the TX line is actually an input. This can be very confusing. In my practical experience, always if you're laying out a board, if you're creating a circuit diagram, if you're laying out a board, allow for 0-ohm resistors, allow for some method on that circuit board to reverse the TX and the RX line. A lot or some modern microcontrollers allow to do this in software, in which case you don't have to worry about it. But more often than not, I've seen instances where you've tried checking everything, you've checked all the data sheets, you've rechecked the circuit board, and it still got wrong. So yeah, that is kind of the curse of the UART connections of the RS-232 connections, for example. That very often RX and TX are exactly in the wrong spot. RS-232. Many people probably have heard about the RS-232 standard. It was the first off-board intended or medium distance, not really long distance, but medium distance serial bus. Really, it's a point-to-point. It was really intended as a point-to-point connection. But it is often, because it has the multi-drop capability, it is often called a bus. So RS-232 was designed at a time when differential drivers were not a thing, when differential drivers were not possible easily in hardware. Transistors had just been invented, transistors were becoming common, but really they were trying to increase the signal-to-noise ratio of a single-ended communication line that was supposed to go off-board. Usually RS-232 is being defined or is used up to 15 meters of cable length. If you use a lower speed, often you can run it for a longer distance. But generally 15 meters, 20 meters is probably the longest that you should run an RS-232 cable. Beyond that, one should think about switching to a different type of interface. So RS-232 is an asynchronous, single-ended, point-to-point interface for off-board communication. It is pretty much the only interface that I'm talking about here that is single-ended and still designed for off-board. And it's not great, but it was historically designed for that. And what they tried to do in order to increase the signal-to-noise ratio was the designers of this interface, they increased the voltage. The original definition for RS-232 has a voltage swing from up to minus 15 volts to plus 15 volts. This is not often being done anymore, but it is definitely defined as one bit state is a negative voltage, and that is a 1. So 1 is the signal level 1 is used as a negative voltage, and the bit for 0 is a positive voltage. This has the effect that if you are working with an actual RS-232 interface, lots of industrial devices still use actual RS-232 interfaces. They can be detected by the standard 9-pin D-sub connectors. If you take a multimeter and you check out and you measure the voltage between ground and the pins 2 and 3 in this case, the one with the negative voltage in idle mode, the one with the negative voltage will be the transmit line at that device. It's just a quick check. If one wasn't sure which pin is the transmit line. It is pretty much obsolete. RS-232 is obsolete. It was part of most PC interfaces up to the 1990s. But it is still frequently used, and you can still, most importantly, you can still go to AliExpress and purchase and buy USB to serial converters that will implement the RS-232 interface, including the voltage levels for the RS-232 interface. It uses push-pull drivers, an increased voltage level for higher signal-to-noise ratio. Again, this was done because differential drivers didn't exist at the time. It is usually point-to-point, but can be used as a multi-drop bus. It's normally used as point-to-point. RS-45 and J1708. RS-45 defines electrical characteristics of an asynchronous, differential, bidirectional master-client bus for off-board communication. So I'm just like unpacking this here. Asynchronous, meaning it is operated by the UART peripheral inside a microcontroller. We're using the UART for this. It has a differential signal line, so it operates in signal pairs. It uses 2 lines, but the signals are also ground referenced. Sometimes I see people not connecting the grounds, and often this works because the differential drivers that you can purchase, the transceivers, the RS-45 transceivers, are pretty good, but even though the signals are differential and subtracted from each other, there are still both signals, the A and the B signals, are still referenced to ground. So technically, it requires a signal pair, a wire pair, and a ground connection. So it's the differential bidirectional half duplex. And in this case, it has 2 dominant bit states, meaning if you're implementing pure RS-45, you would need to follow a very strict timing regime. If the microcontroller is the master, the bus master for RS-45, which in most cases it would be, then the microcontroller, after issuing a command to, for example, a sensor, it would have to vacate the bus within a very specified period very quickly. Basically, after the last stop bit has been clocked out, right away, the driver has to be disabled, the transmit driver needs to be disabled, and the transceiver needs to be put into receive mode. So in order to avoid bus collisions, that is a timing problem. It's not really a problem. It used to be a problem with older microcontrollers because the UART implementation was not telling the software when the last stop bit was clocked out. The UART implementation was telling the software when the transmit register was empty, but the transmit register was empty before the last stop bit was being clocked out. So that was a problem with those microcontrollers. 8051s were part of it. Modern microcontrollers, the STM32 period, the STM32 series, they have features, including automated features, that will turn off the transceiver right after the last stop bit has been clocked out. So in modern microcontrollers, these issues that I'm mentioning are not really a problem anymore. It's a master client bus, so there must be a master. Usually the master is issuing commands and then either transferring data to a client or getting data back from a client. And it is intended for off-board communication. I probably should point out that the RS-45 drivers are very robust, and they can go, the maximum length of RS-45 is substantial. Depending on the cabling that's being used, RS-45 can go up to 1.2 kilometers, 4,000 feet. And that is the official, that is the more or less official specification. Really, if you drop down the speed, you can run RS-45 for kilometers. If you drop down the speed, then you can also run RS-45 on less than ideal cabling. And that makes it useful. If, for example, in cases where not a very high data speed is required, and when I'm saying not a very high data speed, I mean, for example, 19,200 bits per second, 19.2 kilobits per second, 38.4 kilobits per second. That is, of course, a fraction of what Ethernet can do. But Ethernet can go 100 meters, and then you have to switch to something different. RS-45 could run for kilometers. So if, for example, if you are in a old factory and there is old telephone cabling between buildings, and you just need a sensor temperature result, or you need a sensor, some kind of sensor signal that you need to transfer from one building to the other building. And there are unused telephone wire pairs in cable ducts somewhere. RS-45 can do that. RS-45 can deal with bad cabling. RS-45 can deal with long distances, if necessary, kilometers. RS-45 can do things that other buses don't normally do, but at the same time, it's also not as fast. Two dominant bit states, so both levels, the 0 and the 1 level, are both driven. RS-45 is the basis for several industrial buses. I mentioned that before. Modbus, for example. The problem here is that the bus itself, the bus protocol itself, has to be implemented in software. This is not really a big problem because most microcontrollers, at some point in time, somebody will have written drivers for software drivers for an RS-45 implementation, but it is something to be noted. J1708, I wanted to mention. It is not a popular bus anymore. It was popular at some point. It's a modification of RS-45. It is compatible to RS-45. That means if you're setting up a J1708 system, You can buy an USB to RS-45 converter, and it can read the signals, the data signals that you're sending from your microcontroller um, on that you're preparing as a J1708 style signal. So it is somewhat it's compatible with RS-45, but it is not fast. There is a trick here, and that is if you look at the picture on the right-hand side, there's a standard RS-45 transceiver. There are many possible RS-45 transceivers. Every large semiconductor company has an RS-45 transceiver in their lineup. And these transceivers all have the same pin out. They're all 8-pin devices. They have the same pin out. They're mostly interchangeable. They're cheap. They're easy to get. It is really not a special bus in terms of cost. It is, or it can be the cheapest possible bus to be implemented if an off-board solution is required. What they did in J1708 is they are using the transceiver, the transmitter enable line to actually transfer the data. You see this little inverter symbol that is right next by the TX line. That used to be an actual inverter that the circuit designer had to be implement there. In modern microcontrollers like the STM32 series, you can invert the output signal from the transmit line just by clicking a checkbox. It can be inverted in software. So you don't need this inverter in hardware when using those microcontrollers. What that does is it creates one dominant state and one recessive state. The recessive state is implemented by the pull-up and pull-down resistors R1 and R2. I don't really want to go in further detail here. It is quite a clever design. What it means is there is no collision. If you're using J1708, you don't have an error state. I mean, of course, it is possible for two transceivers to start transceiving or to start sending at the same time, and that is technically an error condition. But it doesn't create the short circuit currents that you would get with a pure RS-45 driver. So the J1708 implementation is an implementation to be used when low power consumption, when you need an off-board bus that is differential and can go a long way, but at the same time that is very low power. That is a benefit of J1708. Even in an error state, it won't draw 50 milliamps or 100 milliamps. The worst case that's happening in an error state is that your data will be garbled. And then you just have to make sure in your protocol that you detect that the data was wrong and that you can request a data packet. But that is all just done in software. Okay, I am getting to the SPI interface. SPI interface is a synchronous single-ended master-slave serial bus with two unidirectional data lines. The clock and data lines are typically driven by push-pull output stages. Again, I'm unpacking this here. Synchronous, it means it has a separate clock line. It is single-ended, it means it is intended to be it doesn't have built-in error correction, and it is intended to be on the same circuit board together with the microcontroller. It is master-slave, or master-client. Typically, the microcontroller is the master, and there's a number of peripheral devices that are the system clients or slaves. And the microcontroller will connect to these devices and send data or receive data. It is a serial bus, and it has two unidirectional data lines. It has a clock line, two data lines, one for receive, one for transmit. Um, it's typically driven by push-pull output stages, which is not an issue here. So it creates for each data line, it creates two dominant states, but that's not an issue because the lines are unidirectional. It just means that these data lines can be very, very fast if necessary, because both zeros and ones are actively driven high and low. If you look at the picture to the right, you see how simple it is. The picture is the upper picture on the right, because it is essentially just the slave peripheral device. It's essentially just two shift registers that are connected in a circle. The signal lines are very characteristic. MI, MISO, MOSI, SCK. So that is master in, slave out, master out, slave in, and serial clock. Those are the typical names for an SPI. If you have an unknown, if you look at a schematic and you have an unknown serial interface and you don't instantly know what type of serial interface it is, if you see anything that says MISO, that means it's an SPI interface. Some microcontrollers use different names now. But the MISO, MOSI, and SCK are the traditional names for these signals. It is one of the simplest implementation of a serial interface. It does not provide error checking. It doesn't need to if it is on the same board, because the environment is under control of the designer. No user can do something bad to the interface. Which it could if it was like on a cable outside of the circuit board. It is intended for onboard communication. It's all called a 4-wire or 3-wire serial interface. We can see why. In the picture to the upper right, we see 4 wires. One that I haven't talked about yet is, in this case, it's called the slave select signal. That's what it's called on the processor. Really on the peripheral device that is implementing this, the device that is talking to the microcontroller or is being requested data from by the microcontroller. On that device, it is usually called the chip select signal. You can see a typical bus system in the picture underneath, where there is an SPI master, and the SPI master is connecting to the SPI slaves and addressing them through a CS that stands for chip select or chip select. It is a separate signal that tells the SPI slave peripheral device that any data on the serial bus is intended for it. Each bus line is selected through its own chip select signal, making SPI uneconomical for large numbers of bus clients. So you can already see in this example, in the picture in the middle, that for every device that is on the SPI bus, a separate select line has to be implemented on the microcontroller, on the SPI master, which is usually the microcontroller. So if you have a lot of SPI devices, very quickly you're spending a large amount of separate pins on the select signals, on chip select signals for these SPI slave devices. That is the drawback. The advantage of this serial bus is its simplicity. And it's also that the lines are the data lines are unidirectional. I am switching over to the next page for this. Here is the setup again. High data rates are possible, only limited by the silicon technology of the SPI devices. SPI speed can exceed the processing capacity of the microcontroller. Again, here the example is that It is just two shift registers that are connected together. And if you clock, generally, you can clock these shift registers as fast as the implemented silicon technology allows. That means on some devices, you can clock these at 10 megahertz, at 20 megahertz, at speed rates where a standard, for example, an 8-bit microcontroller, cannot make use of data that's coming in at 8 megahertz. It's way too fast. So luckily, the microcontroller is a bus master. The microcontroller is determining the speed of the interface. But for example, an embedded flash device, um, I mean, a, a memory device, can support speeds that an 8-bit microcontroller cannot use. It doesn't matter really, but I'm just saying this to point out that the SPI interface can be very, very fast. It's one of the fastest interfaces, onboard interfaces that you can get for a microcontroller. The simplicity of the SPI, of the serial peripheral interface, allows for easy implementation in software. That is the next thing. If you're in a situation, you're designing a circuit, a board, you're with a microcontroller, and the microcontroller has different pin has a pin out that allows for different types of signals on the pins that the microcontroller has. For example, different port pins can be used for PWM outputs, for analog to digital converter inputs. They can be used for UART outputs, inputs. And generally, these pins are capable of supporting a number of different devices. So what sometimes can happen is that all the important devices use up pins that otherwise are being used by an SPI interface that is on the chip, that is the actual SPI interface that is supported by the microcontroller. But the pins are used up. You're using them for other purposes. So now you have the problem you want to interface, for example, an SPI EEPROM or an SPI storage, otherwise storage device. And what you can do relatively easily, you can just take 4 random port pins, GPIO pins on the microcontroller, and you can implement an SPI interface in software. This is called colloquially bit banging. It works very well for the SPI interface because there is no effective protocol. It is just pushing data into shift registers. The code to do this, the code amount to do this is small. The processor doesn't have to wait. You can basically just say GPIO pin up, GPIO pin to 0, and then set the clock lines. There are no wait states. It can all be done without any waits. So there is not much time that is being lost. There is not much processing power that's being lost if you implement it. It is, of course, still vastly inferior to an actual SPI interface module that is on the microcontroller. But at the same time, if 4 port pins is all that you have available to connect to an SPI device, you can do this. So because of its simplicity, it is possible to implement SPI in software. Next item. The SPI has 4 possible operating modes created by variations of idle state and shift and sample edges. I have pointed that out in the next image. That is the middle or the bottom image of the 2 images. This goes into details of how the SPI actually operates. This Going into detail for the SPI bus, that would be worthy of a different presentation. I just wanted to show that you have four different operating modes, because you could have two different idle modes. The line could either be idling at 0, or it could be idling at 1. And you can determine, you could have two different edges, transitions, that indicate the shifting of a bit and the sampling of a bit. So that makes for four different modes. Most SPI implementations inside a microcontroller will support these different modes. And generally, if you see the data sheet for a peripheral device, the peripheral device will also tell you which modes it supports. Next item, because all lines are unidirectional, it is easy to electrically isolate with optocouplers. I should have added here the with optocouplers. And there is no bus turnaround delay. Unlike with a bidirectional or a half duplex line, there is no, both lines are just going into one direction. One of the lines goes from the slave peripheral device to the microcontroller. The other line sends data from the microcontroller to the peripheral device, or to the external device, I should say. So because of this, you can very easily use four optocouplers to isolate a slave device. Where does this come in handy? This comes in handy, for example, if on the same circuit board, you have a need for isolating, let's say, an analog to digital converter. Imagine that you need to measure a very high voltage. So for example, 220 volts. And you want to use an A to D converter for this. And you cannot connect the AC mains power, for example, the 220 volts, directly, because of regulations, directly to your main microcontroller. But what you could do is you could move a SPI A to D converter, analog to digital converter. You could move that to the side of the 220 volt AC and connect this SPI A to D converter through optocouplers to the main microcontroller that is doing the measuring. So sometimes there are useful situations where isolating, or having the option of isolating an SPI device on the same circuit board, makes sense. The last item here. Data is received by sending data. When you're looking through example code, for example, you have an SPI interface for a specific microcontroller, you're looking online, you're looking on Stack Overflow, you're looking for sample code for that processor for SPI implementations, you will frequently see a command that transmits data in a routine in a subroutine that is intended for receiving data. If you look at the first image again, to the top right, the reason for that is because the master needs to operate the system clock in order to get data from the slave clocked back in. So the master needs to transmit data to receive data. So when you are in a subroutine, if you're looking through an example, a code example, and you're looking through a subroutine, and you see a transmission of a dummy byte. The dummy byte could be 0, or the dummy byte could be FF, depending on the idle state of the bus. This is to start a receive process. Even though it says it's transmitting. It is transmitting in order to receive data, because the shift registers are coupled. Applications for SPI. Port expanders. For example, if you don't have enough output pins on the microcontroller that you have chosen, there are specific devices that essentially that can be connected through SPI and that allow you to connect more GPIO pins to your microcontroller. One of them is the MCP23S17. I should point out that these examples of the chips that I'm mentioning, they're supposed to give you a start. You can look at semiconductor distributors. In my case, it would be, for example, DigiKey. You could look on AliExpress. Just type in these chips, like those are some of the most common examples, but they're not the only examples of these types of chips. But if you start looking for these for these chip names, most likely you will find more different chips that are going to pop up, or you will get into a category of, for example, port expander chips, where you can select other port expander chips. The names, the circuit names, the integrated circuit names that I've chosen here are some of the more popular ones. If you type these into a website, you will probably get more hits. They're not the only ones available, but they're intended to give you a start if you're designing your own project. That being said, so port expanders, for example, the MCP23S17, the small TFT displays, in this case, the ILI 9341, TFT displays up to 3.5 inches. The issue here is that SPI can be very, very fast, but it is not fast enough for large displays. Because once you're getting into resolutions of 400 pixels into each direction, you're getting into tens of thousands of bytes that need to be transferred within 5-10 milliseconds. So that's kind of where the limit of the SPI speed is coming up. The ILI 9341 is like one of the chips that supports the SPI port for this TFT displays. If you look on AliExpress if you just search on AliExpress for ILI 9341, you will see a number of 3.5-inch displays that are going to pop up. The problem is, and 3.2-inch displays, some maybe even 4.3-inch displays. But once you're getting into resolution sizes for 5-inch, 7-inch displays, SPI is generally not supported because it is not fast enough for large resolution displays. But if you just want if you just want to have like a small to medium sized display, yes, SPI can support it. EEPROM, NOR flash memory. In this case, up to 256 megabit. EEPROMs, of course, are smaller. Typical examples for EEPROM is, for example, a 93C46. For NOR flash memory is a W25Q128. If you don't know what the difference is between EEPROM and NOR flash, a quick reminder, EEPROMs are typically smaller, partially very, very small. For example, the 93C46 is a 1 kilobit device. It is 128 bytes. Where, for example, the W25Q128 is a NOR flash memory, and it has 128 megabits, so it has 16 megabytes of storage space. You might be asking, okay, if both are interfaced by an SPI interface, why would I not always go with a NOR flash memory? Because it is so much bigger. The reason for that is EEPROMs are being controlled differently. EEPROMs have the advantage of a much, much higher cycle erase and rewrite rate. EEPROMs are typically rated for 100,000 to a million read-write cycles. NOR flash is typically rated for maybe 10,000 rewrite cycles. More importantly, EEPROMs, in EEPROMs, you can address every byte, every storage byte separately. NOR flash memory is written and erased in sectors, or is erased and written in sectors and pages. The effect of that is, if you're trying to implement a larger flash memory, you will have to reserve space for reading, modifying, writing um, bytes or partial pages. You will have to keep at least a page in your memory. So it is supporting a NOR flash memory is more intensive in RAM requirements and is more intensive in code requirements. If you just want to store a serial number, if you just want to store a little bit of calibration data, an EEPROM is usually the better choice. If you want to store a large amount of log data, then of course a NOR flash memory is a better choice. And we're not going to talk about NAND flash memory because that is a completely different interface. Okay, enough talked about memory devices. Micro SD card interface. Many people don't know this, but micro SD cards or SD cards in general have a legacy SPI interface mode. So you can basically write the entire content of an SD card through the SPI interface. There is the image to the right here of an obsolete Arduino processor. It's an 8-bit processor that can actually write data and even implement a file system on an SD card. That is possible. SD cards can be gigabytes large. So you could store a large amount of data, for example, even log data, on an SD card. I, however, do not recommend this because usually environments for embedded systems tend to be rough. SD cards, and especially the SD card holders, are not really meant for a rough environment. If it's part of an engine assembly, if there might be vibrations, I wouldn't expect the file system on an SD card to not become corrupted if it is implemented in an embedded system. What you could do with an SD card is you could, for example, store configuration data. It is a very convenient way of loading configuration data, even text data, on a PC, from a PC onto the SD card, plug the SD card into your embedded device, have the microcontroller read this data from the SD card, and set up calibration data and configuration data. The other way around, you could use an SD card to very quickly transfer log data that has been gathered in a different, for example, in a NOR flash. That would be a very fast way to transfer logging data from a NOR flash to an SD card that can just be pushed in and unplugged and then read by a PC and examined in Excel, for example. So micro SD card has an SPI interface mode. There are SPI A to D converters, and I've already mentioned the possibility of using an isolated SPI interface to read analog data, analog voltages that need to be isolated from the system ground. There are environmental pressure sensors, temperature sensors, BMP 280, 388, for example. Again, these are examples that are intended if you put these names into AliExpress, into DigiKey, into vendor websites, something will pop up that might lead to other devices too. For these devices, they generally have both. They have an SPI interface and they have an I2C interface. And in most cases, you would rather use the I2C interface over the SPI interface. But it does have an SPI interface. Same with accelerometers and gyroscopes. Same thing here. Usually they have both. They have an SPI and an I2C interface. The next item is more interesting, serial interface bridges. I mentioned that the SPI interface is fast. It is so fast that chips exist that use one serial interface, which is SPI, to convert or to implement a second serial interface. For example, the MCP2515 has an embedded CAN controller. So you use from your microcontroller, if your microcontroller does not have a built-in CAN interface, you can use the SPI interface to connect and communicate to a separate chip that can implement the CAN interface. The same thing with the SC16IS762. In this case, it's a separate UART. It's a separate chip that you can connect to through the SPI interface, and it implements, I think, a double UART actually. So, and you can do that because, for example, the maximum speed of a traditional CAN interface is a megabit per second, but the maximum speed of an SPI interface can be 10 megabits per second. So there's plenty of time and for the SPI interface to get the data that's arriving at the CAN chip at the MCP2515. Okay, so much for the SPI bus. I am moving over to the I2C bus. I2C interface is a synchronous, single-ended master-slave serial bus with a unidirectional clock and one bidirectional data line. So here again, we have synchronous. So there's a separate clock line. It is single-ended. So it is, again, similar to the SPI interface. It is intended for onboard, on the same circuit board deployment. Master-slave, similar to the SPI bus. Usually the microcontroller is the master. Serial bus with a unidirectional clock line, just like the SPI bus, but a bidirectional data line. And I had shown the picture to the right, in the middle right before, when we were talking about output drivers. The I2C interface is using an open drain connection. It's using an open drain transceiver, open drain output circuit, which means it has one dominant state, which in this case is driving to ground, driving to zero. And it has a recessive state for 1, which is being pulled up with resistors. There's a number of characteristics that are happening here that are defining the I2C bus because of this. I'm just going through my items here, my points here. It is intended for short distance communication between MCU and peripheral circuitry. I have to say that, or I have to add to this, that the I2C bus is the more likely bus to be used for a limited off-board configuration. I had mentioned that onboard and offboard usually means the environment, the noise environment is under control of the developer, of the circuit designer. As long as the cable, the wiring environment remains under the control of the designer, short off-board connections are relatively common for the I2C bus. In particular, so for example, what would you do with that? What you would do is, For example, you have a large industrial piece of industrial equipment, and you want to somehow put a device onto this industrial equipment that contains a serial number that can be read by an embedded system, or you want to store calibration data. At some point in time, this big industrial device has been calibrated in some way, and you want to store this calibration data with this piece of industrial or connected, attached to this piece of industrial equipment. And you could do that, for example, with an I2C EEPROM. You just need essentially 2 wires, of course, plus power and ground, so 4 wires. And as long as the impedance of that line and the length of that line is controlled, is defined by the developer, using I2C for short off-board connections is a relatively common occurrence. It is also called a 2-wire serial interface. Obviously, because it has the serial data line and the serial clock line, 2 wires. Clock and data lines are driven low by open drain outputs, pulled high by pull-up resistors. Bus voltage levels can be variable. This is an important item. On many microcontrollers, even if the microcontrollers were intended for 3.3 volt operation, on many microcontrollers, the pins that implement the I2C interface are 5 volt tolerant. Because the microcontroller is not actively driving the high state is pulled by those pull-up resistors. Those pull-up resistors can connect to 3.3 volts, or they can connect to 5 volts. So it is possible to use 5 volt I2C external devices with a 3.3 volt microcontroller. If you do that, of course, you cannot use this bus, like this would now be a 5 volt I2C bus. You cannot do mixed, you cannot do combinations of using 3.3 volt external devices together with 5 volt, with 5 volt external devices. You would have to reserve 2 separate I2C buses, one for 5 volt and one for 3.3 volt. But I'm just pointing out that generally look at the data sheet, check out the data sheet of that microcontroller that you're intending to use, and more often than not, the pins that are intended for I2C lines are 5 volt tolerant. The pull-up resistors. So the limits the maximum data rate. Standard speed is 100 kilobits per second. There's a fairly common, there's an extended speed rate of 400 kilobits per second that many devices support, which is still slow compared to the SPI bus. Again, the SPI bus can go to megabits per second. The I2C bus is comparatively slower, and the reason for that is are those pull-up resistors, because those pull-up resistors have to overcome the cable capacitance, and usually the pull-up resistors are somewhere between 4.7 and 2.2 kilo ohms. Standard speed is 100 kilobits per second. 400 kilobits per second is fairly common. There are faster modes, but those are not very common. Because this is now a bus that is using a bidirectional data line, a protocol had to be implemented. You will also have noted that the addressing is different. The SPI bus used a separate pin, a separate line, the chip select line, for addressing the components on the bus. This is not the case with the I2C bus. The I2C bus, the microcontroller will put the address of the intended device as the first byte, or 7 bits, on the line, on the data line, and clock that in, and the device that has this address will then respond with an acknowledged signal. I don't want to get too much into the details of the I2C bus here. I just want to point out that the I2C bus, so this is now a protocol. This is not just two shift registers like the SPI bus that are basically connected in a circle. This is a protocol that has states. There's a state where the address is being sent. There's a state where it waits for the acknowledge. There's a state where a command is being sent. There's a state where a response is being expected. This is a more complicated protocol. Because of this, trying to bit bang, trying to implement an I2C bus in software is a lot more complicated than trying to bit bang an SPI interface. That is one item. The other item is the addressing. The addressing is done in a very different way. The devices have fixed the typical I2C devices have fixed base addresses that have been given to them and that are absolutely fixed. They're embedded in the silicon of the device that are given to them by the manufacturer. You can vary the base address. Typically, there are 2 or 3 pins on the package of this device, of the I2C client device. And depending on how you define those pins, if you tie them to ground or if you tie them to a positive supply voltage, you can create different addresses. But if, for example, if there are 3 pins for varying the base address, you can have a maximum of 8 of these devices on the bus. That is a drawback. The advantage, of course, is that you just need 2 pins. 2 lines. You just need the clock line, the data line. There is no further address line on the bus. There is no chip select line. The fixed address can be adjusted by the input pins. Yeah, because the addresses are displayed or are addressed by 7 bits, there can be up to 128 client devices. In practice, of course, it's generally less because they all have to have different addresses, and the addresses are given by the manufacturer. The base address is given by the manufacturer. And just like the SPI bus, there is no error checking. So it is originally intended as an on-circuit board bus that is short distance and very close to the microcontroller. Applications. The same, similar to the SPI bus, there are port expanders. PCF 8574, MCP 23017. Note, please note that this is very similar to the SPI port expander, and it is just without the S in the chip name. Small organic LED displays, 1.5, 2 inches or so. EEPROM memories, just like with the SPI interface, you can find EEPROM memories for even larger ones for the I2C interface. What you will not find large NOR flashes with I2C interface, simply because the I2C interface, by its nature, because of the pull-up resistors, is a slow interface compared to SPI. It is a slow interface, and it makes no sense to have a 60 megabyte or larger flash memory where it takes a long time to read. With the I2C interface, it would take a long time to read out the data. The SPI interface is much faster. Um, these serially interfaced NOR flash chips have an SPI interface and not an I2C interface because of the slower speed of the I2C interface. There are A to D converters. There are digital to analog converters. Current sensors, which is basically high side, low side current measurements, DC current measurements. Environmental sensors, pressure, temperature, humidity. I wanted to point out the differential pressure sensor just because drones and unmanned airplanes or aircraft are often very much in the news. For example, if you go to AliExpress and you're looking up for a differential pressure sensor, in this case, for example, the MS4525, you will probably see, or you will probably get a lot of hits for this differential pressure sensor in combination with a pitot tube, which is intended for airspeed measurements in drones. For the standard non-fixed wing drones, having airspeed is kind of like a nice thing to have. For fixed wing drones, airspeed is what keeps the drone in the air. Airspeed is what determines the sink rate. So for implementations like that, a differential pressure sensor is absolutely necessary. And in particular, or this device or similar devices are generally interfaced by I2C interfaces. And they are not too slow. This is data that changes in the range of milliseconds. So if the I2C interface at 100 kilobits per second at 400 kilobits per second is very much fast enough, even though it is technically a slow interface, but it is very much fast enough to read out data from pressure sensors, even from drones in flight for airspeed measurements. Similar thing with accelerometers and gyroscopes. Semiconductor gyroscopes, of course. Also, these two are very popular examples where you will find breakout boards and on AliExpress everywhere. The MPU 9250, there is an MPU 6050. Those are devices that are available on breakout boards. And these devices also measure the acceleration, they measure rotation speeds in speeds that are milliseconds, like 2, 3, 5 milliseconds per measurement value. And the I2C interface can easily keep up with those read rates. Real-time clocks, for example, the DS3231 is a very accurate real-time clock. Also, you will find breakout boards for that device. The DS1307 is not that accurate. The DS3231 is temperature compensated. So, for example, if you needed accurate time, you could combine a DS3231 and connect it over the I2C interface with a GPS module. GPS modules are traditionally interfaced through a UART. This is historically because GPS modules used to be away from the computing circuitry because they had to be on the roof. They had to be off board, a significant distance off board to have sky view. So because of that, GPS units traditionally use a UART interface, asynchronous transmission. Even though nowadays you buy them as a module and they go into the same circuit board. So you could have an I2C interface to connect to a real-time clock. You could use a UART to connect to a GPS module and get a very accurate time from the GPS module and set the real-time clock with this very accurate time from the GPS module. The advantage I'm not just suggesting this because it's an interesting experiment. The advantage of this is if you do that, you do never need to set the time. You don't need a display to set the time. You don't need a keyboard to set the time. The time will be set by the GPS module and available to the rest of the circuitry without needing a user interface and without requiring the user to actually actively set the time. Okay, I'm moving on to the CAN interface. The CAN interface is an asynchronous serial bus with differential signaling, one dominant and one recessive state, and half duplex operation. Asynchronous CAN is a CAN is a multi-master bus. That is what makes it special. The CAN bus has an inherent collision detection that is based on message priority. That depends on bit timing. The capability of having of CAN of being a multi-master bus, meaning any node in a CAN bus system can start transmitting whenever it feels like it. And the negotiating system, if a collision occurs, it is non-destructive, as in the message that the bus or that the CAN node with the higher priority is trying to send will not be destroyed. If a node with the lower priority is also trying to send a message at the same time. This whole system depends on the CAN implementation, the CAN engine inside the microcontroller, checking bit for bit if it has lost prioritization. Because of this, the maximum length depends on the bit rate. The maximum length of the CAN bus connection. What I mean here is if you have a very high bit rate, for example, the maximum speed that the standard CAN is rated for, like which is 1 megabits per second, the maximum length of the CAN bus is just a few meters, because the travel time along the bus of the electrical signal cannot be longer than a certain maximum time, because within every bit, the CAN engine is checking if its message is getting through, or if the message that it's trying to send has lost the negotiation, if it has lost the prioritization. So if you have a slow bit rate, if you decide that your CAN bus doesn't need 1 megabits per second, your CAN bus could work at, let's say, 10 kilobits per second. Instead of having a maximum length of, let's say, 20 meters, you can have a maximum length of 2 kilometers. So if the designer was in a position where the CAN speed can be dropped, that means that the CAN bus itself can be a very, very long bus, similar to RS-45, like in physical length. Multi-master, half duplex. This is similar to RS-45, except because there's one dominant and one recessive state. We again don't have the problem that if two nodes are trying to send at the same time, there is no short circuit. There's a collision, but the collision doesn't result in increased driver currents. However, saying that, CAN is a fairly power-hungry bus because of the termination resistors. You will see in the picture on the upper right-hand side that the CAN bus is intended to have 120 ohm termination resistors. The termination resistors are typically required for, on many buses, our termination resistors are required to avoid bus reflections. This is the reason for this is transmission line theory, which I'm not getting into here in this presentation. But in addition to having the ends of the bus terminated by termination resistors, in addition to avoiding reflections, the termination resistors are essentially enforcing the recessive state. They're pulling the bus towards the zero state. So they must be installed. Because they must be installed, you have an effective resistance on the bus of 60 ohms that the driver has to overcome if it wants to send a signal, which means in active mode, when a driver is sending a signal in active mode for short periods of time, the driver can use 40, 50 milliamps, which is for an embedded systems device, which is a fairly power-hungry serial bus. So the CAN bus is very robust. The CAN bus has built-in error checking. By the time that a message arrives in your data buffers, you can be pretty much sure that the message is valid. There is no extra CRC. The CAN engine has CRC built in. There is no extra CRC and software required. So the CAN bus, if the microcontroller has a CAN transceiver, has a key and CAN interface, a CAN engine, it is a very convenient bus to use. But one has to be aware of the limitations. And one of the limitations is it can be fairly power hungry in terms of 50 milliamps, which was not a problem for the situations that the CAN bus was designed for. The CAN bus was designed for an automotive environment. And in automotive environment, 40 or 50 milliamps are absolutely not a problem. CAN bus, I mentioned that the CAN bus data lines can be very long. CAN bus is supported by a number of drivers in higher end devices, in embedded Linux devices, in there are PC drivers. CAN bus, the typical data rates are 500 kilobits per second, megabits per second, 250 kilobits per second. It is not uncommon for a system to have two different CAN buses, one high speed and one low speed system in an automotive environment, for example. The CAN bus philosophy is that the messages are very, very short. Each message is has a maximum of 8 bytes. And the idea of the CAN bus is it is a bus in an automotive environment to transfer or to send data, important data, to send data very, how can I phrase this? It is not a bus that is intended for large amounts of data. It is a bus intended for critical signals, for critical data. Data can be exquisitely prioritized through its message IDs. It is short data that can be prioritized and sent very, very quickly. So, for example, you have a brake that is malfunctioning, and the brake controller has to tell the main engine control unit that a brake is malfunctioning. So that message will get the highest priority, the highest message ID, which actually is the lowest message ID, but that's just because 0 is the dominant state. In this case, the logical 0 is the so it is meant for that kind of environment where there are short messages of high priority that have to be sent very, very quickly. Because the CAN bus is also very convenient to use. In other environments that are not automotive, people decided this is a bus that is very useful, and but we want longer messages. So there are a range of implementations that are sitting of software implementations that are using the CAN engine that make node addressing and sending of large amounts of data easier. Okay, that is the general information about the CAN bus. Really, if I had to go into the details of the CAN bus, the actual bit timing, that would be a whole different lecture. I just wanted to point out the CAN drivers. There are two separate CAN drivers that I have as images. The TGA 1051T3, it's a very common CAN driver. That one has the advantage that it can, the output lines and input lines that are connected to the microcontroller can have a different voltage level than the CAN bus itself, or the CAN driver itself, I should say. In this case, you see the VIO line. The VCC can be 5 volts, VIO can be 3.3 volts. Why would you do that? It's because of what I mentioned about the current consumption, because very often you want to separate the power domains. You want to separate the power that goes to the CAN controller from the power that goes to the microcontroller. If the microcontroller is using 3.3 volts, it sometimes uses these 3.3 volts as a reference voltage for its A to D converter. So you don't want to introduce large jumps in this 3.3 reference voltage because the CAN controller is suddenly demanding 50 milliamps or possibly more, maybe 70 milliamps. So you want to decouple the 3.3 volt power from the CAN controller. And that's where this is useful. That's where having a separate VIO input can be useful. The other CAN controller that you see on the right is a CAN controller for 3.3 volts. Those are also not common. Most of the time, CAN controllers are intended for 5-volt operation. Again, those are just chips that I'm pointing out that you can use as a start for a search if you're doing your own project, that you can use as starting point for a search for the ideal CAN transceiver, sorry, not controller, CAN transceiver, for the CAN transceiver that best fits your best fits your application. Most CAN transceivers have the same pinout. You can see that here between those two examples. One is an NXP device, the other one is a TI device. Both use the same pinout. It's pretty much a standard pinout. This is similar to RS-45 drivers. You can have 10 different manufacturers of RS-45 transceivers, and they will all have the same pinout. I have two examples. I'm not entirely sure if we have time for this. I think we have actually gone past the times that I had intended. Professor Kovalenko, should I continue on with the two examples that I have here, or do you want to stop the presentation here?
Thank you for the question. Maybe we should ask Mr. Piskarev, Alexei Nikolaevich. Because I see the timeline and we time to time lost some people due to schedule because we have almost a day here and of course lessons for the students, other lessons.
Yes, yeah. Yeah,
Maybe we start. We should stop here for today and continue next time, if you don't mind.
I don't mind at all. Like I didn't look at the time. Yeah, it is way later than I had expected. When I started out the presentation, I wasn't sure how long it would take. I would have been happy if you had interrupted me. I hope at least it was somewhat interesting for the students.
Uh-huh, uh-huh. So, your decision is to stop here, yes?
If you're telling me that we're out of time, then yes, my decision is to stop here.
If you don't mind, let's stop here because we slightly out of time and
Yep. Okay.
we may lost more people in next several tens of minutes.
Yep. Okay.
Aha, so thank you for the brilliant presentation. Please feel free to ask Volker about any aspects you heard today. Будь ласка, питання, шановні здобувачі.
Yes, I have a question. It's it's about the peripheral device. Can we connect a microcontroller to a high current device, no, such as electrical motor drive, relays?
Yes, absolutely. Um, there's a whole range of motor control options that you can use to control an electric motor. What kind of electric motor do you have in mind? How big is it? A DC motor? Is it a big AC motor? The easiest, of course, would simply be using a relay. Do you just want to turn the electric motor on and off, or do you need speed control?
Just on, or no, turn on and off.
Yes, you would use a relay for that. A relay, do you know what a relay is?
Yes, this is electromechanical device.
Yes. You can of course also use a solid state relay. So you can use a MOSFET, for example, or there are IGBTs, there are MOSFETs that can be used for this if you do not like an electromechanical device. It also depends on that motor. Is it an AC motor? Is it meant for 220 volts or higher? Or is it a DC motor for 12 volts or 24 volts?
So let's say it's be DC motors.
It's a DC motor. Okay.
Mhm.
If you were using a DC motor, I would probably either use a MOSFET or an integrated driver. What kind of current are we talking about? Is it 2 amps? Is it 5 amps? Is it 10 amps? Is it bigger?
I'm not sure about that, no, but is much bigger than microcontroller can provide.
Oh yes, oh yes. So for example, in this example that you see, example 1, port expansion, this was just an example that I implement or that I intended to demonstrate a shift register, how a shift register can be used for port expansion. But in the schematic that you see in ULN 2803. Can you see that or?
It's the Darlington arrays, no, microscheme.
Oh, okay, that's too bad. It's so basically there are different types of drivers that you can attach to a microcontroller output. You can also connect a MOSFET directly to a microcontroller output. Depending on the current that you need and depending on the way how you want to interface or how you want to connect that motor, a typical on-off method is to use a low side driver. A low side driver is essentially just a transistor or a MOSFET that is connected with its emitter, like if it's a transistor, a bipolar transistor, that is connected with the emitter to ground. The base goes to the microcontroller with a current limiting resistor, and the collector is connected to the motor, and then the motor is connected to plus 12 volts. That would be one way, but in order to find the best way, I would need to know what kind of output currents are required. How big is the motor? What voltages does the motor have? There's one thing that I want to add. If it's a DC motor, then it would be very easy to not just turn it on and off. It would be also very easy to speed control it, because every microcontroller has a PWM output. The way how typically an electric motor, a DC motor, is speed controlled is by using PWM. Sorry, PWM means pulse width modulation.
Okay, are you satisfied with the answer?
Yes, yes, I am.
Thank you. Next question, please. If you have. We have a question in chat. Do you see the chat, Volker?
Just a second, I'm just opening up here.
Okay, I can read.
Okay, I am not seeing the chat mesh. Oh, wait a second here. Can modern microcontrollers effectively use multiple interfaces simultaneously? And if so, how can conflicts be avoided? Yes, absolutely. In particular, I'm mostly talking about the STM32 series of microcontrollers. That's what I'm most familiar with. Modern microcontrollers have something that's called DMA, direct memory access. So it is not just that the modern microcontrollers are a lot faster than microcontrollers used to be. The 8-bit microcontrollers were kind of limited in speed to like 16 megahertz clock frequencies, maybe 20. The modern 32-bit ARM-based or Cortex-M ARM-based microcontrollers are not just a lot faster. It's not uncommon for even cheap microcontrollers to be running at 80 megahertz, at 160 megahertz. In addition to that, they also have a whole range of tools that can be used to relieve the core processor of unnecessary work, of unnecessarily moving data around. One of these tools is called DMA, direct memory access. And you can set up, for example, UART, you can set up SPI, you can set up the I2C interfaces. It's probably easiest to do with SPI and also UARTs, so that data will be coming in and collected in specific memory areas on the microcontroller and can then be processed in blocks. With the difference being, otherwise it would have to be, the processor would be interrupted like in previous processors. Every time a byte arrives, the processor gets an interrupt and has to drop everything that it's doing and has to process that byte. DMA makes it unnecessary. So yes, modern microcontrollers are fast, and they have built-in tools that can deal with large amounts of incoming data. So yes, those conflicts can be avoided.
Thank you. Please, more questions if you have. I think, thank you from Maria in chat again. Please, questions. It seems like no other questions. Yeah, no questions. So